All right, hello Math 110. This is the first video lecture I'm recording for our class, and I hope all of you are doing well. I know these are unusual and trying circumstances, and we're all going to do our best here. I'm actually, this is in my apartment in St. Louis, so I have a whiteboard here, and I will be recording these video lectures and posting to my YouTube channel, which I sent a link to you guys. The idea of that is to look at those lectures before our class time. And again, our class time will consist of a Google Hangout Meetup video conference, but I want to record this lecture for you guys to give you an idea of the topic we're covering. It's been a long spring break, 2 weeks. Let's see if we can rub the dust off our understanding of math this semester. I believe before spring break we were talking about exponential and logarithmic functions. Today we're going to consider an important application of exponential functions, and that application is to population growth. So the topic today is population growth. Okay. Let's remind ourselves, because it's been a long time, what does it mean to have what is an exponential function? An exponential function is something that looks like, as an example, 2 to the x is an exponential function. What makes that an exponential function is the variable x is in the exponent. You have a numeric base, constant number base to a variable exponent. This makes this function exponential, and if you look at the growth of an exponential functions grow at an ever-increasing rate. They grow very rapidly. It turns out population growth is actually exponential in nature. And I'm going to consider a couple problems with you guys, but first, let me talk about, give you guys a table. I'm going to create a table here of 2 different types of growth. And one of these types of growth is arithmetic. Let's look at it and leave enough room here. I'm adjusting to a very small whiteboard here, but I'll do my best. The next type of growth is geometric. And let's suppose both of these types of growth start with 2 individuals. Okay, arithmetic growth means you keep on adding 2 every generation. So this is our generation. This is Gen 0. Okay, then we have generation 1, 2, 3, 4, 5. Okay, these are our different generations. And if a population grew arithmetically, the next generation you'd add 2 plus 2 is 4. You'd have 4 individuals. Then the next generation you'd have 6, you'd have 8, 10, and 12, and so on down the line. A geometric population, instead of growing by a constant amount 2, you multiply each generation by 2. So if we had Gen 0 had 2 individuals, we'd multiply 2 by 2 and we get 4 for our next generation, which is the same as an arithmetic growth so far. But then now what we do is we take 4 and multiply by 2 and we get 8. Okay, so the second generation under geometric growth would go to 8, multiply 8 by 2, we get 16, 16 by 2, we get 32, 32 by 2, we get 64. 2 different types of growth. Both are growing, but one is growing arithmetically. Arithmetic is a slower growth rate. Geometric is a faster growth rate. Geometric growth rate is exponential. This is exponential in nature, and it turns out that populations actually grow exponentially. They don't grow arithmetically. So that's our topic. This is the introduction to our topic, and we're going to now consider an example problem, which has to do with the world population. We'll do a couple examples. These lectures I'm going to make them a little quicker than I did in class. There's not any class participation at this point, so we're just going to, I'm going to kind of not go as deep as I might in the previous, before this whole coronavirus thing came up. So anyway, but I think that makes sense to me. It turns out we can model the world population with this equation. The growth of the world population with this equation, okay? Is this an exponential equation? Yes, it is. Our variable t, let me write down what these things mean. N is the world population. N0 is the initial population. Okay, R is the growth rate. and t is the time, okay? Time is the variable here. So what this equation tells us is how does our population grow as a function of time, okay? And this is an equation we can use to model that growth rate. N0 is our initial population. R is the rate of population growth. T is the time. T is the variable because T is in the exponent. This is an exponential equation, and this models population growth. And let's actually apply this to our world population. In 2019, the world population was 7.7 billion. Okay, someone is playing music downstairs. If it's a little bit annoying, after this lecture, I'll have to go tell them to quiet that down a bit. So we have 7.7 billion people in the world in 2019, and the world's growth rate of the population was 1.12%. Okay, that's the world's growth rate. In 2019, that means the world grows by 1.12% per year in population. Let's ask ourselves, what will the population be in 2050? What is our population in 2050? Okay. The way we will do this is we have to figure out what our time is, and we use this N0 as our initial population. So the population in 2050, we're looking for N, will be equal to 7.7. I'm not going to write the billion part, 7.7. But we'll just write 7.7. That's our population in 2019. Okay. And then we plug in 1 plus R. So now we're going to plug in our growth rate. Be careful though, our growth rate is not, we don't plug in 1.12, we plug in 0.0112 for our growth rate. We have to convert this to a decimal, and that means we divide by 100. So we don't plug in 1.12%, we plug in 0.0112 as our R. Then we raise it to the t power. Well, what is t here? T is how far in the future is 2050 from 2019? Well, that's 31 years. So t is 31 years in the future from 2019, and that means we plug in 31 for t. Now we can simplify this. This equals 7.7. We're going to add 1 plus 0.0112. We get 1.0112, right, raised to the 31 power. And this is going to give us our world population. You guys can check this in your calculators. This comes out to 10.9 billion, okay? 10.9 billion people in 2050. We currently have 7.7 billion. All right, let me talk about a couple caveats to this. One thing to be aware of, there's a couple assumptions here. One assumption is the world population grows exponentially. And that's the assumption today. In reality, populations eventually can't grow exponentially forever because if you imagine you had a desert island and you had a population growing, eventually you would run out of space and natural resources, and that would limit your population growth. So world population can't grow exponentially forever. We'd simply run out of room. But this is a good assumption at this point in time. Another thing we've assumed is the rate stays the same over time. This is not necessarily true. The population growth rate can actually change. Fortunately, it's going down slightly. So every year, the world population is growing, but it's growing by a smaller amount every year. The rate is coming down, which is good. I think we have enough people on this planet at this point. So just be aware of that. Okay, I want to do a second part of this problem. So I'm going to erase this board. We'll see how this works. This board is kind of shaky. It's sort of not really attached to the wall because I don't want to drill in. This is an apartment. I don't want to drill into the walls here, but we'll see how this goes. Let's do part B here. Part B is, and I'm going to write down our basic equation again. N equals N0 times 1 plus R to the t power. We're going to do a part B here. Part B is, when will the world population, how long will it take to double? So we're going to ask ourselves, how long does it take the world population to double? How long to double for the world population? Okay, so here's how we'll do this problem. We're going to start with this equation. Now, in this case, we know our initial population, or our population in 2019 is 7.7 billion, right? 7.7 billion. We want to figure out how long it takes to double, okay? Well, if the population doubles, that means that the population will be 2 times this amount. So our future population in this case, will be 2 times 7.7 billion, okay? And that's going to be 15.4 billion. Okay, that's our future, that's the world population when it has doubled from its present value, okay? So what we do in this problem is we can now plug in 15.4 billion for n, so now we have 15.4 billion for n, okay? We plug this in our equation, our n0 is 7.7 billion, okay? And our growth rate, if you recall, our growth rate was 1.12%. Okay, 1.12%. The growth rate, we'll assume it remains the same. So we can plug in our growth rate. We get 1 plus 0.0112, remembering to convert our growth rate into a decimal. Okay. Now the unknown in this problem is the time t. So t is an unknown. Okay. And in this case, what we want to do is solve for t. We want to solve for t. How long does it take this population to double? Okay, given these parameters. And the way we're going to do this, and this is where you guys will have to wipe the rust off what we did with logarithms way back 2 weeks ago before all this craziness. Okay, we want to find the value of t that makes this equation true. The way we do this, the first step, if you guys recall, is we're going to divide both sides of this equation by 7.7. So I'm going to take 15.4 divided by 7.7 equals 7.7 divided by 7.7. Combine these two terms, that's 1.0112 to the t power. Okay, this cancels out. It turns out 15.4 divided by 7.7, that equals 2. So this equals 2. We get a new equation, 2 equals 1.0112 to the t power. Okay, that's our equation. We want to find the value of t that satisfies this. And now, here's the key, folks. This is where we're going to go back, put on our logarithm hat from way back 2 weeks ago. Hopefully you guys haven't forgotten everything about logarithms. The way we solve this equation is we take a natural log of both sides. So we'll take a natural log of 2, and this will equal a natural log of 1.0112 to the t power. Okay? And this is what we get, all right? And then we're going to use the special property of a log. If you take the log of some letter m to the n power, there's a property of logarithms. If you guys remember, we talked about this, which means you can pull this n forward, pull this in, peel this in out in front, pull this in front, we get n times natural log of m. Okay, so in applying this to this case, we get natural log of 2 equals, now when we pull this t in front, we get t times natural log of 1.0112, okay? So I've just used this power property to pull this t in front of the natural log. Okay, and are we still recording? Make sure this is the first time for this, so I'm still getting used to this setup. And now I want to solve for t. The way I solve for t is I'm going to divide both sides by natural log of 1.0112. Natural log of 1.0112. Okay, and then I get, that isolates t. These cancel out, and I get t equals natural log of 2 divided by natural log of 1.0112. Okay, and then now it's calculator time. I can plug this in my calculator. And if you plug in your calculator, you get 62.2 years. So at the current world growth rate, it's going to take the world population 62.2 years to grow to double in population. Now, if we start in the year 2019, that'll be 2019. We'll round this off to 62 plus 62. Okay, what does that give us? That gives us 2081. Is that right? 2081 is the year in which the world population will double. Assuming it continues to grow at this rate, my hope is that rate will go down, and so it'll take longer for our world population to double, if it ever doubles. I don't really want it to double. we've got enough people on this planet. This is a simple case of applying exponential equations. This is an application of exponential equations to model the growth of the world population. Let me just talk about one more problem. I'm going to erase this board, and I'm going to do one more example with you guys with populations. By the way, on Wednesday as well, we're going to be talking about population growth as well. So 2 days of population growth. Let me just talk a little bit about fertility rates. Fertility rates. Fertility rates have to do with how many children come out per couple. If you guys think about it, if every couple, a fertility rate of 4 children per couple, fertility rate of 4 children per couple means that, is that population going to grow or stay the same? It's going to grow because you have two, in a crude way, you have 2 people coming in, you have 4 coming out for every generation. And so this population would double every generation because you'd have 2 parents and 4 kids. Each one of those 4 kids will go out and say they marry and have 4 more kids each. So each generation you're getting a doubling, okay? And in this case, you can model the population with this equation. Don't worry a lot about where this equation comes from. If you wanted to, I could talk more about it, but just kind of take my word that this is the equation you get, okay? This is for a fertility rate of 4 children per couple, okay? I'm going to do an example problem where we have 2 populations. We have population A. Okay, population A has a fertility rate of 2 children per couple. 2 children per couple. Okay, and then population B has a fertility rate of 4 children per couple. Okay, and let's say population A has an initial population, okay, has an initial population of 90,000. So let's say P0 equals 90,000 for population A. Population B has an initial population of 10,000, okay? Okay, what's going to happen to these populations over time? Well, population A has a fertility rate of 2 children per couple. That means that for 2 people coming in, you get 2 out on average, which means there's no population growth. So this population, population A, will just sit 90,000 forever, okay? Population B has a fertility rate of 4 children per couple, which means that every generation you double the population. So population B will definitely not stay at 10,000. It will grow exponentially from 10,000. At some point, population B is going to surpass population A, okay? Because population A stays at 90,000. Population B stays at 10, or it doesn't stay, it grows from 10,000 and up and beyond that. At some point, population B will pass population A. The question is, when does population B pass A? When does population B pass population A? Okay, when does that happen? When does that happen? Okay. Well, let's apply this equation here to population B. Okay, so if population B stays at 90,000 and population A grows from 10,000, then when population B reaches 90,000, that's when it will pass population A. So when population B grows to 90,000, then it will be equal to A, then it will pass A. So population B will pass A when population B equals 90,000. So if we take this equation, in this case for population B, okay, right, our P will equal 90,000 when population B passes population A, okay? We know that our initial population is 10,000, okay? And what we can do now is plug in our equation. We get 90,000 equals 10,000 times 2 to the 0.04t, okay? So this is now our equation. What is this equation doing? It's saying, it's an equation where we can find the time it takes population B to pass population A, okay? And what we could now do is solve this equation. We divide both sides by 10,000, okay? And this leads us to this equation. We get 9, because 90,000 divided by 10,000 is 9. 10,000 divided by 10,000 is 1. We get 9 equals 2 to the 0.04 t power, 0.04 times t. This is not 0.04 to the t, it's 0.04 times t. We want to solve this equation for t. Guess how we do it? Any guesses? I wish you guys were here so all you guys could chime in and say, we take a natural log of both sides. So we take a natural log of both sides. If we do that, we get natural log of 9 equals natural log of 2 to the 0.04t, okay? At this point, we again utilize the power property, and that means we can peel off the exponent part here. So we can bring this 0.04t power in front, and we get a natural log of 2. This all equals natural log of 9, okay? And then we want to isolate t. We want to isolate our variable t. Okay, the way we do that is we divide both sides by 0.04 natural log of 2, 0.04 natural log of 2. Okay, these all cancel out. So now this leads us to this beautiful thing where we get t equals natural log of 9 divided by 0.04 times natural log of 2. That's a beautiful thing. This is our solution for t. Okay, if we now plug in our calculators, I'll spare you guys that time, but you could do it. If you plug in your calculators, you get 79 years. So, for two populations, one which is 90,000 and stays the same, another population which starts at 10,000 but doubles every generation, every 25 years, by the way, is a generation, but doubles every generation, that second population will surpass the first population in 79 years, or about 3 generations, a little over 3 generations, and population B has caught up to population A, okay? So this is a great example of applying exponential equations to model human population growth. Again, does human population always grow exponentially? Typically does until you run out of space or room. Sometimes the rate will change, but this is a good example of this. So this is the conclusion of this little video lecture. I'm now going to post this to my YouTube channel. Hopefully you guys find this helpful. Again, the idea is to look at these lectures before class, and then we come together in class, we'll have a video conference, and you guys can ask me questions about what we did. We can just kind of talk about it a bit, just kind of check in. Anyway, it was good seeing you guys, and I'll see you next time for the next video lecture, which will be posted well before Wednesday's class. All right, hope you all are well. See you later.